This is the Andromeda Galaxy. I mentioned it to you last time. It's the furthest, most distant object you can see with your own unaided eye. When you look at it, it won't look like that. If you look at that central portion like that, that's about the size of the full moon in the sky. This thing is big, but it's dim. It consists of 10 billion stars, all going in a circle like that. Yes, I know, you can see some stars. That one, and that one, and that one, and that one, and that one. This is going to come across in the webcast. I can't use my laser pointer. So let me point to some stars with a little pointer here. That's a star, and that's a star, and that's a star, and that's a star, and that's a star. But none of those stars are in the Andromeda Galaxy. You look at this picture, and you're tempted to see this central region here, which is what's the size of the full moon, and all these other wonderful stars. And in the background, you see all these other stars, right? Well, no, they're not in the background. Those are in the foreground. Those are in our own Milky Way. And this star is really close. That's why it's so bright. This star is pretty far away. That's why it's so dim. This little one here is even dimmer. That's why it's so little dim. But it is pointing up there, isn't it? Yeah. Okay. But they're in front of this thing. Whoops. Sorry. They're in front of this thing. You're looking past them like a dirty window with little spots on it. That's our own Milky Way, and this thing is behind that. That was Hubble's first great discovery, because he looked at this thing with a powerful enough telescope and care. He was interested in it. Everybody thought it was a bunch of gas. It was called a nebula. And it still is. Some people, it's often referred to as the Andromeda Nebula. Nebula was basically a bunch of gas. But it turns out not to be what you're seeing here is not the gas. You're seeing lots of tiny little stars that are so small that with a typical image like this, unless you go to really high magnification, you don't even see them. This is this plate-like collection of stars, similar to what the Milky Way is. These stars out here are all the stars from our own Milky Way. This is another galaxy. Fewer, probably under 1 billion stars in that one. It's a satellite galaxy. It's probably orbiting this one. Okay, we have one too. It's called the Large Magellanic Cloud, discovered by Magellan, discovered for Western European civilization by Magellan. People down south knew all about it. And I mentioned that a satellite galaxy like that, sometimes I like to fool people and I say, this is a photograph of our own Milky Way galaxy taken from a distance of, well, it actually was taken from a distance of about 3 million light years. Well, it would have taken us 3 million years at the speed of light to get out there to take the photo. So we're not likely to get any good photos of the Milky Way unless we discover a giant mirror out in space and can look at ourselves. Actually, there is a possibility. I call it the Thurston universe. It was first presented to me by Bill Thurston, a renowned mathematician. He wondered whether or not the universe maybe isn't as big as we think, but actually consists of little regions of space like a room. And then when you go to the wall of the room, you actually come in the other side. And so universes are really quite small. But as you walk over there, you pop out the other side, and it's a different topology, they call it. This is rather speculative. And as I spent some time, several decades ago, trying to figure out how to measure this, if this were the case, then light being emitted by the Milky Way would come to this wall, reappear over here. This is mathematically possible. And if it's possible, why doesn't it happen, right? So it would come in the other way, and then we'd be able to see ourselves. Except we'd see us the way we were maybe 100 million years ago. We'd actually be able to look at the Milky Way. And maybe that's what we're looking at here. No, you can pretty much rule that out. This has too many stars. But an interesting speculation. We're getting into the realm of speculation here. No, you don't got to know that for the final. But it's fun to talk about, fun to think about. The fact that as I walk this way, poof, I'm gone, and I reappear over there. How would I know? Light goes that way, it comes this way. I think there's room over there. It's actually what's behind me. Fun speculation. Science fiction, almost. We can't rule it out right now. You want to do experiments and look for that. But this is the Andromeda Galaxy. Now, in winter, it's almost overhead. And what you see when you look up at it, if you look around, and if you learn some stars, if you can find the North Star, light here for a moment. find the North Star. And you could, lots of ways to find the North Star. You could find the Milky Way, and then the pointer of the North Star points to that. And then there's this galaxy, this constellation called Cassiopeia. It looks like a big W. And if you sort of go this way and go 1.5 times as far, the Andromeda Galaxy is right over there. And as I said, it's about the size of the full moon. But it's dim. It looks just like the Milky Way. You can't see it in Berkeley because there are too many lights scattering sunlight, there's too many lights whose light scatters off the atmosphere from street lights and buildings and so on. And it brightens the sky a little bit, just enough so you can't see the Milky Way or the Andromeda Galaxy. But this thing is up there. Get out into a really dark area. Good excuse to go up to the mountains in winter. Here you are skiing, and instead of going out partying with everybody else, go outside, get adjusted to the light, stand there freezing, look up in the sky, and look for this fuzzy patch. My daughters fondly remember me taking them out into the freezing cold in the nighttime and looking up at this fuzzy little patch, and you're seeing something that's millions of light years away, the most distant thing you can see with the unaided eye. And are you really seeing it? It's just a fuzzy patch up there about this big with a long exposure. So you can see the dimmer parts of it. Your eye can't because we don't let enough light into our eyes. With a dimmer exposure, you begin to see this. And it's called a spiral galaxy because the arms, it seem to be these spiral arms that go around. And those are regions where stars are still being formed. It's a beautiful thing, especially in the photograph. I was an amateur astronomer for a while and got disappointed that I could never see anything as pretty as the photographs. Other amateur astronomers love to take beautiful photographs. Of course, they're never quite this beautiful. So after building my own telescope, I kind of lost interest in that. Now, there are lots of these galaxies. And I was asked at the beginning of class what's in between them. And the answer is not very much that we can see. Let me go to this one here. And what I'm going to do is the same trick. So this one is called Virgo cluster. I'm going to close it. And then I'm going to open recent. Virgo cluster, and now it'll fit the window better. Oops. Okay. So this is an image of one of the nearest clusters of galaxies. What does this mean? That means that right now the Milky Way and the Andromeda Galaxy, they feel their own gravitational attraction, and as a result, we're part of a cluster of about 17 galaxies known as the local cluster. It only has 2 really big members, Andromeda and the Milky Way. But there are lots of little things like this, like the little one I showed you off of the little satellite galaxy. There are about 17 altogether. And they're held together by gravity, and they're moving around each other. It's almost like a little solar system, except it's not flat. It seems to be sort of three-dimensional. And as you look away, you find other clusters. Most galaxies seem to be parts of clusters. And the clusters, by the way, seem to rotate around other clusters. These are called superclusters. So there is this sort of structure, and right now one of the most interesting areas in astronomy is trying to figure out how it got this way. As you'll see in this lecture and the next one, we now know the universe is about 14 billion years old. 14 billion years ago, stars did not exist. Now stars exist, and they're arranged in galaxies, and the galaxies are arranged in clusters, and the clusters are arranged in clusters of galaxies. And how did we get from an era when stars didn't exist into that structure? That's a really interesting issue for theoretical astronomy. A lot of it's being done on computer simulations, trying to make little models of the early galaxy, of the early universe. By the universe, I just mean everything. Everything that we can see. That's what we now refer to as the universe. In some old books, they would refer to a galaxy as an island universe. But the terminology has changed, and now we refer to the universe as everything. When people talk about parallel universes, we're saying, is there some other structure as big as ours with everything that we can't see because it's in some other parallel dimension? But this is what's called the Virgo cluster. And if you look at this thing, maybe lights down again, really dark so they can see this better. We'll make it, yeah, that's good. Dark, 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 real dark. In fact, maybe I'll even turn this power off. Okay, and now as you look at this, you see, oh, here's a big, big galaxy. It doesn't look like the other one. This one looks sort of fuzzier. This is sort of, it's called an elliptical galaxy. It doesn't really have those arms in it. This is given a name, M86, because an astronomer named Messier catalog these things. This is one of the ones that he saw. This one here, too, is an elliptical galaxy. A lot of stars, but they're not so organized. It doesn't seem to be quite as flat a plate. But this is a galaxy here. This one looks like it's either small or further away. These are actually all about the same distance. Another galaxy, another galaxy. This is actually a galaxy, too. Most of these are stars. But those stars are actually foreground stars, of course. They're in front of this. Even though they look like they're in the background, they're actually in front of it. But the ones that are actually galaxies that have been identified as galaxies here are named. They're given numbers, NGC numbers, New General Catalog numbers. These are things astronomers know. This is a catalog of galaxies. Some of the bigger ones have their old names associated with them. They actually have new names, too, but this one is called Messier 84. And amateur astronomers sometimes log galaxies in the same way that a bird watcher will log birds. You know, they want to see every one themselves. And the Messier catalog is within reach because they were all discovered with relatively small telescopes. So this is what it looks like. But now we can take a small region, a really tiny region like this. Well, actually, maybe a little bigger than that. And let's take a really long exposure. So if we do that, and this was done a few years ago, it's become a very famous image. What happened here? I thought I was turning this off. Okay, so now you're taking a small region, and in fact, let me turn that on because I want to take a quick look at. Don't keep that image up there. Just want to take a look at this. Okay, so imagine you're doing the following. I just want to check this number. Hey, you. What's going on here? Cut that out. Okay. Imagine that I'm holding a dime right now. And you are the average student in this audience. So you're not at the back, you're not at the front, you're sort of average. But I'm holding a dime. But I'm holding it really, I'm holding it up. And behind me is the sky. Now, that's a small region of the sky. It's much tinier than the full moon. But that's the region of the sky in the next photo I'm going to show you. A really long exposure, because if you look at that, you'll find there are almost no stars in it. You're now looking at an area that's small enough that if you're looking through the thin part of the Milky Way, there'll be maybe one or two stars in it, but almost none. But now, so you see blackness. But now you take a really good telescope, in this case, the Hubble Space Telescope. I'm not showing you this image yet. It'll be up in a moment. You take the Hubble Space Telescope, so it's in space. That means there's no atmosphere to get in the way, and that helps a lot. Secondly, you take a long exposure, several days. So even dim, distant galaxies get into your picture. They call this deep space. Deep meaning far away, but deep also meaning profound and shocking and amazing. So I'm going to show you this. I'm going to have to go through the same cycle again. Okay, let me just do this again. Let me just bring that one back for a moment. Let me move this over here. Go here. So this one almost fits, but let me close it and bring it back. There it is. There's that dime. Now, what do you see here? I said there'd be no stars in it. Well, actually, I think there may be a star in it. Where is it? Oh, this, I think, is a star right there. And this is a star, so that's 2. I think it's a star up there. I can tell it's a star by this diffraction pattern that you get off the telescope. And from that, I can identify that it's actually a point-like object that's overexposed. But there are no other stars. What are all these things? They're galaxies. Once I hold the dime up to the sky, and you look at a region that small, you've run out of stars in the Milky Way, at least when you look through the thin part of the Milky Way. But as you look at distant space, you see these galaxies. I mean, look, every spot you see, except for the ones I mentioned, can be identified as being galaxies. You see more galaxies in space than there are stars in the Milky Way. This photo, I think I put up on the website. It may be in the book. It was done by NASA. It's in the public domain. It's an amazing photograph. People look at this, and they're looking, and not only are they looking at the distant part of space, but there's something else they're doing. The light coming from this region took hundreds of millions of years to get here. That means we are looking at a part of the universe, not the way it exists today, but the way it existed hundreds of millions of years ago, before any animals even crawled on the surface of the earth, when all of life on Earth was in the sea. And this may even be older than that. I have to check my numbers on that. But at least that old. So we're looking at in the past. True, it's a distant past. But we're looking in the past, really far past. In fact, astronomers love the thought, we have the lights back on now, that as we look out in space, we're also looking back into the distance, in distant time. And this is strengthened by a number of observations that as you look at these old galaxies, and you look at the stars within them, and then you look at the stars that are in our own galaxy, there are great similarities, but there are some differences. For example, our own stars look like they've burned more of their fuel than these old stars. Of course they have. The stars in these distant galaxies are hundreds or billions of years older. We're looking at them when they were still young and fresh, whereas ours are old. Then you start looking at how many stars there are, and how many galaxies they are, and what kind of galaxies. And astronomers have come to the general principle now, which is still partly assumption, but is a working assumption that has proven very effective, that the distant parts of the universe are really basically the same as our part of the universe. It's not really different out there. We're just looking at it the way it was 1 billion years ago. And that means we have, if on making this assumption, it actually has a name, it's called a cosmological principle, but it's actually just an assumption that is based on the ability to see these differences as changes that are taking place. It works remarkably well. In fact, no matter where in the universe we look, everything we can see, every distant part of the universe that we see, appears to be the same as simply a younger Milky Way. So this is now the current belief, substantiated by a lot of data, that the universe is basically the same everywhere. There's no region out there that's empty. There's no region out, well, there is between the galaxies, but that what we're seeing is part of the universe that's very similar to ours. If we were living off there in this Hubble Deep Field region, we might be taking a class in physics for future presidents. I mean, the odds are pretty small, but there's a lot of space out there. And that things out there are basically the same kind of stars, same kind of everything. That enables astronomers to look back into the past. Now, looking back in the past is a little bit of an exaggeration. When you listen to my lectures, you're looking back into the past. You're not hearing me, you're hearing me the way I was a few billionths of a second ago. Right? Actually, the sound even takes, sound goes 1,000 feet, basically 300 meters, 1,000 feet in a second. Goes 100 feet in a tenth of a second. You're hearing outdated lectures. They're a tenth of a second slow, except for those of you in the front. And those of you in the back have it even worse. And those of you who are listening on webcasts, even worse. So you're looking back into the past. Not much, though. You look at the sun. Sun, 150 million kilometers, 93 million miles away. Take the speed of light. Goes 1 foot in a billionth of a second, basically 1 foot in a computer cycle. That's pretty slow. I mean, it used to be considered fast until you guys all got gigahertz computers, and now that's not so fast anymore. But that's how fast light goes. To get to us from the sun Takes 8 minutes. Suppose the sun blew up, completely disappeared, or maybe released all of its energy at once. We wouldn't know it for 8 minutes. Maybe it happened 7 minutes ago. This is on its way. We would have no way of knowing because signals can't travel faster than the speed of light. And light doesn't travel faster than the speed of light. And we're looking at the sun. Well, we're not looking at it right now, but we feel sort of warmth from the sun and everything and no explosion. But that just represents the way the sun was 8 minutes ago. You should know that, 8 minutes for the sun. The moon is about 1 second away in terms of light. Okay, a little bit more. I think it's 1.3 seconds. I have the numbers written down here. But it takes that long. It's really hard. If you look at the old movie 2001: A Space Odyssey, supposedly it took place in 2001. I remember waiting for that to come. 2001: Space Odyssey, they're on their way out to Jupiter, and nobody can talk to them. They send the astronauts messages, and let's see, I think I have Jupiter here is, let's see if I have the time here to go out to Jupiter. Didn't write it down here, but it's a few hours. Let's see. Oh, here. This is. Yeah, I didn't write the number down here, and I don't remember it myself. Let's see. We know from the Earth to the Sun is 8 minutes. Jupiter is about 5 times as far away, so that would be 40 minutes. That's if Jupiter is the closest it could ever get. If Jupiter is further around on its orbit, it would be a few hours. That's for one-way communication. So in 2001, they take that into account. None of this instant communications that you see in so many science fiction movies. Of course, in the science fiction movies, what they must be doing is warping space so that signals can go through the shortcuts. So that's why I enjoy science fiction movies. So you're always looking backwards in time. And with the sun and the moon, you're looking back a little bit. Let me start going over the universe again. But I'd like to concentrate now on what's in close. We believe that our what do I mean by our solar system, first of all? I mean, here's the Milky Way galaxy, consisting of a whole bunch of stars. We're out here somewhere. There are things, we're moving. We're moving around. We go around once every 250 million years. So we are bound to this. We're orbiting the Milky Way galaxy. Everything else is. Otherwise, we'd just fall into all this mass. We're moving in a roughly circular orbit. That's kind of interesting. How did that come about? And not only that, but we're actually moving up and down a little bit. Every now and then we get a little bit too high, and we get pulled back down, and we're oscillating up and down, like that. It's about 60 million years to go up and down one cycle. You don't got to know that. These kind of details are fun for me, but there's no reason why a future president needs to know that number. But other stars are moving around too. And so they're bouncing around. Now, we're all moving around the Milky Way, but we're not moving around these stars. The gravity isn't strong enough. There's Alpha Centauri, the nearest known star other than the sun. Alpha Centauri is out there, and it's bigger than the sun, and we feel its gravity, but we're not moving in a circle around it because we're moving too fast. We're moving right past it. And the gravity deflects us a little bit, but doesn't make us go in an orbit. So there are all these stars out there close by, and they're all moving past us at a relatively high speed. This is going to be important for a point I'm coming to. So here we are. We look at these stars. They're all in motion. As a group, we're moving around the Milky Way. But we're bouncing up and down, and some are going faster, and some are going slower, and so this is the galaxy. Now, you see a bright star out there. How do you know? How do you measure its distance? It's really hard to do. I mean, try looking with your eyes at the Golden Gate Bridge and figure out how far away it is. How do you do it? Well, you say, oh, a little bit hazy, so it looks far away. You look at the ground in between, and you say, oh, it looks like I would have to travel for a few miles to get there. You may try bobbing your head back and forth, like I do here. See, if I bob my head back and forth, I see you move a little bit. And the people who are close, you're moving a big angle. Where the people who are far away really don't move much of an angle at all. So if I could bob my head back and forth, maybe I could measure the distance to the Golden Gate. It doesn't work very well. Too far away. Works fine with a classroom. In fact, I have two eyes, each one looking at a different angle. And that gives me a good sense for things that are, it's a good enough sense so I can throw a baseball to you. I know about how far away you are. So I can use that to measure, or whether that lion is attacking me. Or this image comes to mind, okay? Because I talked to a friend recently, I'm going to Africa, and the issue was dangerous animals. And most dangerous animal turns out to be the water buffalo, not the lion. And rhinos are mean too. And I, knowing a little physics, I asked Bob Drews, a good friend of mine. He goes to Africa every summer. And I said, look, if a rhino is coming at me, I don't want to run away because he can outrun me. Can't I just wait till the last minute? And as he's charging me, then I go, whoo! And he just keeps on going because he's so heavy. Just to ask him that. Not that I wanted to try this. And I was delighted. But Bob is a director of the museum over in San Francisco. As I said, he goes out there every summer to collect these specimens. And he said, oh yeah, no, I have a friend who does that. He's a rhino baiter. You just, you get bored, go out there, bait a rhino. I'm not going to try it. I still will be teaching this course in the fall. Okay. But using your eyesight, when the rhino's getting close, you can tell how far away it is. That was how I got into that little story. But for distant things, it doesn't work. Now, the way we actually measure the distance to stars is by bobbing the head. Okay? Now, on the ground, you really can't bob the head enough to do that. But as the Earth goes around the sun, as I'm going around the sun, I see the star there, and then I see the star there. Right now, you're to the right of him. I mean, you're there, and he's, look, that side. I go this way, on the other side of my orbit. Hey, you're on the left of him. You must be closer. I can tell how close you are. As the Earth goes around the sun, you photograph the stars, and the stars that are close will appear to be on one side and then the other. That's called parallax. And that's how we measure the distance to the stars. Same way our eyes, but we use the orbit of the Earth to do that. It's really not easy to measure the distance to the stars. Now, once you've measured the distance to a few stars, then you can look at that star and see how bright it is and make a good guess for more distant stars, because the more distant stars will be dimmer. If they're the same kind of star, which you use by spectral fingerprinting. You look at the light that's coming out, you look at the colors that are coming out. If the colors have exactly the same ratio as some other star, then it's probably a very similar star, and then you can tell how far away it is by how dim it is. If the colors are shifted a little bit in frequency, that's the Doppler shift, then you can tell whether it's moving towards you or away from you. So these are the tools that astronomers use. Once you get past the nearby stars, the bobbing of the head around the solar system doesn't work anymore. You can't measure the distance to the Andromeda Galaxy by that effect. It's too far away. Like the Golden Gate Bridge for my two eyes. Just too far away. We have to measure the distance to Andromeda by looking at the brightness of the stars. This is what Hubble did. And he discovered this thing was not nearby. It was really far away. It was not a cloud of gas. It was a galaxy of 10 billion stars. He did that by looking at the brightness of individual stars. It was the only way to measure the distance. Now we have several other ways. Zach? Okay, are the ones in the that look red because of the redshift? No, I don't think so. I don't think those were that far away. I believe the galaxies that were red in the red picture were red because they have a different kind of collection of stars. Basically, red giants, young stars, made it red. But I'm not absolutely sure of that. That's my educated guess. So here we are in the solar system. We're bobbing around. Bright stars are probably close, so you look at them and you measure their parallax. It's actually a lot of work to measure the parallax, because even for the nearby stars, the parallax you get is usually less than 1 arcsecond. That's 1/60th of the resolution of your eye. You need a pretty good telescope and very precise measurements just to measure the distance to the nearby stars. So we do this. We've measured the distance to all nearby bright stars. Suppose there are nearby dim stars. How would we find them? Well, you can measure the parallax. Great, let's do that. When will we do that? When did we do that? The answer is about 2010. We have not measured the distance to most stars out there. We really haven't. There are some projects coming up, Pan-STARRS and maybe LSST, that will measure the distances to all these stars. We haven't done that because it's so much work, and now these are automated telescopes that will do the job. So the fact is, we don't know the distance to most stars. We really don't. Surprising fact. Why bother? Who cares? Well, you'd like to find the stars that are nearby. So how can you do that? Well, we found a lot of stars that are nearby, but we don't do it by measuring the parallax. We find the stars that are nearby because of the fact that we're moving. And if I want to find something that's nearby, the sun is moving pretty quickly. And I look at it and I say, oh, there's someone who's nearby. I think, well, actually the angle's not changing very much, but whoa, that's really changing fast. He must be nearby and you're far away. And that's actually how we find most nearby stars. Because of the fact that the sun is moving, as we look at a star and look at it a year later, it's in a different position. Ooh, it must be a nearby star. So that's actually what we do. Then, even though it's dim, we think it's nearby, now we measure the parallax. We haven't had the time to measure the parallax of all stars, but we'll pick the bright ones and we'll pick the ones that seem to move during the year. That's called proper motion. I can imagine a multiple choice question on proper motion and parallax. Remember what parallax is. It means as we move around the sun, the Earth, we look at something from 2 different directions. Whereas proper motion means we're actually using the fact that we are moving fast through space. So nearby objects will change from year to year. Every year they'll be a little bit further down that way. With parallax, they go back and forth and back and forth. Parallax is very, very, very precise. Proper motion is hard because if something's moving by me at an angle, I have to know how fast it's moving before I really know how far away it is. But we detect the stars. We notice that they're close because of their high proper motion. This is all building up to a theory for which I became infamous in 1984, called the Nemesis theory. The Nemesis theory was based on, and this was in the news recently actually, was based on an idea that I had. Wound up collaborating with Mark Davis and Pete Hutt on this. And the idea was maybe as the sun is moving through the galaxy, here's the sun. Okay, let me draw a bigger picture of the sun. So over here is the sun. And going around the sun is the Earth and Jupiter and Pluto and these other planets. And there are also things called comets that I'll talk about. And these things are all moving in orbit around the sun, all held by gravity. They are the solar system. So the solar system is those things that are really permanently attached to the sun. Now over here is another star. And it may have its own planets. According to Jeff Marcy has discovered that most other stars have planets around them. Really a remarkable discovery of recent years. And maybe comets, although that's harder to tell. We don't really know that for sure. We don't really understand how our comets were made. And they have not been observed around other systems. There's been dust seen around other stars. Maybe they have comets, maybe they don't. I'll tell you more about comets as we get on. And these stars are all moving past us. So even if they're dim, we notice them from the fact that our relative motion is so high. You take astronomical photos, take them a year later, you lay them on top of each other. Most stars are in the same place. The nearby stars seem to have moved. That's called the proper motion. So that's how we notice nearby stars. Or if the star is really bright, we'll notice it and measure it just because, hey, you're going to measure stars, you might as well measure the ones that are bright. And so those are the ones we measure. There aren't so many of them. They're nearby, and so those are measured. Now imagine the following. Imagine there is another star right here, or maybe even right here. And that star is orbiting the sun. Well, that would be closer than any other star. So certainly we would notice it, right? Wrong. Why wouldn't we notice it? This is something that was my inspiration for the nemesis theory. I recognized it wouldn't be noticed. Why wouldn't it be noticed? It's close, so it must be bright. Well, it's close, which means it's brighter than it would be if it's far away. But by far, the most populous star in the Milky Way galaxy is something called a red dwarf. This is the most common type of star in the galaxy. It's smaller than the sun and dimmer than the sun. If there were a red dwarf star here orbiting the sun, would it be so bright that it would have made that list of stars to measure? The answer turns out to be no. It'd be too dim to be seen without a good pair of binoculars. So it wouldn't have been noticed because it's bright. Well, okay, but there are two ways we notice nearby stars. One is because it's bright. The other is from the proper motion, as it's zooming past us. But this isn't zooming past us. We're moving with it. And so, yes, it's orbiting, but according to the theory that we came up with, it takes 26 million years to go around once. That means it's going very slowly. And as a result, the idea was we wouldn't have noticed its parallax. We wouldn't have noticed its brightness. We could be part of a double star system, and we never would have noticed. Strange but true. Well, let's say this, it would have been a 50% chance of noticing it, something like that. Now, why? So the three of us wrote a paper in 1984 suggesting that the sun is part of a double star system. Isn't that kind of odd? It turns out that 2/3 of all the stars in the galaxy are part of double star or multiple star systems. It's a really common thing. Many of you may have seen this newspaper article that came out just a few days ago about Sedna, in which they mentioned my name, because Sedna is a new planet of our solar system, or maybe it's a comet, not really clear, in a rather peculiar orbit. And there was a theoretical explanation that maybe this peculiar orbit can be accounted for by the fact that the sun is really a double star system as proposed by Richard Muller. And this was in the news just in this last week. Look up Sedna, look up Muller, look up Nemesis on Google, those three words. You'll jump to this article about that mentions me. And it may even be true. It's been a long time, over 20 years, since I proposed the Nemesis theory, along with Davis and Hutt. And it hasn't been found, so most people have lost interest. But I know that we haven't done the searches yet. I tried doing the search myself, wound up wearing out a telescope trying to do it. And, but there are automated telescope systems being built now in Hawaii. The Pan-STARRS system is being built, being funded by the Defense Department in order to search for possible things that might hit the Earth, possible impactors that could cause a problem. So they're being funded by the Defense Department, but they will also look at all the stars and measure their parallax, and they will find this other star. Running this paper, I remember reviewing it before we submitted it and saying, you know, we have a unique opportunity here. We could name this thing. And if it's really there, of course, this will become part of history. Now, how often do you get to name something that is a part of history? So what comes to my mind? Yeah, we can name it Muller. No. What else could we name it? I came up with several names. I'll tell you, I haven't told you why I thought it was there yet, but the reason was that it was responsible for killing the dinosaurs. So I thought a good name would be George. Right? Anybody see the connection? Which saint slew the dragons? St. George. Okay, anyway, I stuck that in, and then I thought of another name. I thought of Shiva, the god of death and destruction. And then I thought of Nemesis, the Greek god whose role it was to make sure no creature got too powerful on earth and threatened the gods in Greek mythology. And here the dinosaurs were getting so powerful, something had to wipe them out, so I thought Nemesis. And I wrote these 3 names into our paper and expected Pete and Mark to say, you can't put that kind of stupid stuff in. And actually, they kind of liked it. So we sent it off to Nature. Nature then edited it a bit. And the paper, they thought the paper was too long, so they cut out a few things. They cut out George, and they cut out Shiva. Later, of course, Stephen Jay Gould suggested, oh, they should have named it Shiva. They are so Eurocentric. We tried. But Nature picked one of the 3, and it was Nemesis. And since then, my name has been invariably associated with Nemesis, with the Nemesis theory. So this little companion star now has the name Nemesis, if it's there. And we'll know within the next few years, because pan-stars will measure. See, the star, if it's there, is already photographed. It's in the photos, just nobody realized it was close. That's because they didn't measure its parallax, and there's no proper motion to speak of. Now, why did I think Nemesis was there? This will be my claim to fame. They'll forget everything else I did in physics if Nemesis is discovered. And if it's not discovered, within the next few years, then if Pan-STARRS really does a search and doesn't find it, then it's possible it's hiding because it's not really a star, but it's a black hole or something like that. Oh, baloney, At that point, I retract the theory. I'm not going to save it by making it exotic. It's supposed to be, most stars are multiple star systems. Maybe the orbit of Sedna was affected by this in the early part of the solar system. Now it's out there because most star systems, they gradually get scattered out and they get further and further away. And now the main role it has was in killing the dinosaurs. So let me talk about that, the genesis of the Nemesis theory. I can't imagine anything less important to a future president. And Big Bang, maybe, just for conversation after dinner. If you're the president and you bring up Nemesis theory after dinner, they'll say, oh, that was that stupid theory by the guy named Muller that was disproven 20 years ago. It actually wasn't disproven, but when you don't discover something, people assume it was disproven. Okay, so the origin of Nemesis theory is the following. 2 paleontologists, Jack Raup and Dave Sapkowski, Jack Sapkowski and Dave Raup, looked at the extinctions as a function of time. So they're looking to see how many creatures really went extinct. And they made an infamous plot that was published in 1984. And the plot showed 250 million years ago, there was a huge number of extinctions. Everybody knows about that. It's called the Permian-Triassic extinctions, or the PT extinctions. And that was really famous. There were also extinctions 65 million years ago. And those were actually disputed. That's when the dinosaurs went out. But was it a sudden event? That was disputed. Well, they found a bunch of others. They found another one there, and there, and there, and there. And when they looked at it, they said, this is odd. It's a regular pattern. In fact, there was a peak every 26 million years. Amazing. This has been debated by the statisticians ever since, including myself. Did they really find something there? Okay? Because nobody could come up with a good explanation for it, people said it was a statistical fluke. There's some chance, if you have random events, that they will look like they're coming in a regular period. I took on the challenge of trying to explain what could cause this, and eventually, I had a lot of theories. I went to see Mark Davis, and he suggested moving up and down in the galactic plane, so we worked that out, and it doesn't work. So we came up with other ideas. That didn't work. Finally, we got together with Pete Hutt, who was visiting, and we explained all the ideas, and he said, oh, that one will work. Well, how could that work? Oh, let me show you. We put it all together, sent out the publication. It's actually the only explanation that, in my considered opinion, is still a viable explanation. There were lots of people who published the theories that we rejected. And then we had to write what sounded like, your theory doesn't work, mine does, articles, which journals don't like and people don't like. But we had already thought of those theories and had rejected them. Anyway, this one is held up, and here's the way it works. So this will tell you a little bit more about the solar system. And we knew that this one came from the impact of an asteroid. But I said, no way, it could be a comet. We needed it to be a comet, not an asteroid. But I was intimately familiar with the experiment, with the data, and I knew that we could not distinguish an impact from a comet or an asteroid. So I said, oh, it could be a comet. Now here's the way it works. So here's the sun. Here's the Earth going around it. Here's Jupiter. Okay? Now, out here, it turns out, are all the comets. Comets are chunks varying in size from the size of Pluto, which many people now think is really a comet and not a planet. But you can't say that because it makes little children cry. And the reason it makes little children cry is every little child loves Pluto, because Pluto's the little one, right? So astronomers have gotten into deep trouble by suggesting that Pluto is not a planet, that it's only a comet. Now there's something called Sedna, which is a comet. Turns out to be bigger than Pluto. So is Sedna a planet too? If you make it a comet, what is it? Anyway, just don't bring up this issue with little children in the room. There are all these comets here, and interesting about the comets, let me give myself some free space here. Oh, boy, this is so many things to discuss. Okay, let me go quickly on this because I do want to get to some of these other subjects. Okay, so here's the sun, and here's Jupiter, and the Earth is in close. And here are these comets. And the comet orbits, some of them go in almost circles. Some of them go like this. They go in every which orbit. All sorts of crazy orbits. Why do the comets have such crazy orbits? The reason is that nearby stars pass by. When a big star passes by, it affects the sun and the Earth together. But these things are way out there. It may affect this one a lot more. So the comets get all scrambled up. You don't have to understand this whole thing. There will not be an essay on it. They get all scrambled up. So every possible orbit has comets in it. Now, Jupiter is also pretty massive, and any comet that comes close feels the gravity of Jupiter and either gets pushed into the sun or kicked out to infinity. So the result is there are comets going almost everywhere, except not in the inner solar system. The inner solar system is vacuum clean by the effect of Jupiter. So I call this the eye of the comet storm. And it's a good thing. Because if Jupiter weren't cleaning this up, we'd be hit by comets basically, every million years, maybe even sooner than that in the early solar system. And when that happens, it's so disruptive that life would have had a really hard time. So we're in this region kept clean by Jupiter. Now, suppose a star goes past. Then it affects all the comets again. And now what happens is some of their orbits change and they come in again. And that'll happen for a few million years until Jupiter kicks them out. But during those few million years, there are a huge number of comets here, and one of them will hit us. Now here's the idea of the Nemesis theory. That this star that's coming past is not actually coming past. It's part of a big orbit going around the sun that comes close every 26 million years. Worked out the numbers, it works out okay. If such a star existed, we call it Nemesis. Then every 26 million years, the eye of the comet storm would get filled in, and on average, by a billion comets, with a billion comets in this region, on average 1 or 2 would hit the Earth. Do great destruction. And then life would recover. On one of these, a particularly big one hit the Earth, killed all the dinosaurs, except for the birds. Question? Oh, is there evidence comets have hit other planets? So you look at other planets like Mercury, you find it's pockmarked with craters everywhere. The only reason you don't see so many craters on the Earth is that because we have an atmosphere and we have geology and plate tectonics, but the moon is covered with craters. Mercury is covered with craters. You see craters on almost every other planet except the ones that are covered with gas like Jupiter and Saturn. So yeah, there's lots of evidence. We've even seen comets go into the sun. So these impacts take place, and we see how many comets are out there. We know they should take place. But this was a way of explaining it. To do that, we had to postulate the existence of Nemesis being in orbit. And that's the Nemesis theory. And it will be proven or disproven or paid attention to again if it's discovered, which should happen with Pan-STARRS sometime in the next 5 or 6 or 7 years, I hope, assuming Pan-STARRS goes ahead at its full speed. And Chapter 1 talked about the impact and the energy release and the explosion. And at this point, you could go back to Chapter 1 and fully appreciate what we were talking about back then. And this class is taught by iteration. Rather than the Euclidean structure where we try to build up on basic principles, we get to the stuff right in the beginning. And then eventually at the end, you can understand it. Let me get back to the galaxies at this point. Because there are lots of things we don't really understand. Maybe I'll move over here. I mentioned the galactic clusters. Here's a galaxy. We saw Virgo. Here's a galaxy. Here's a galaxy. Here's a galaxy. Here's a galaxy. There are all these galaxies. And you can look at the galaxies and see how much they weigh by counting the stars. You can also know how much they weigh by, as the stars move around the circle, you know they're being held in by gravity. So you can calculate how much gravity is there, and from that you can calculate how much mass there is. And an odd thing happens. When you do that, you find that there must be something other than the stars in a galaxy. We know what stars weigh. We know that because the Earth goes around the sun. We know the gravity of that. So we know the gravity of the stars. But as we look at the galaxies and the fact that the Earth goes around like this, we add up all the stars, it doesn't add up. There's something else there. What is that? We don't know. What do you do when you don't understand something? You give it a name. So it's called the dark matter. Why don't we see it? Well, actually, it turns out if it were made up of bricks or planets, we wouldn't see it. It's hard to see things in astronomy unless they glow. We've yet to see directly a planet going around another star. We can tell there are planets there by the fact that the star is wobbling. But you don't see the planet itself. Things that don't emit light are hard to see because the starlight shining on them isn't nearly as bright as the stars. So mostly what we see are shining stars. So this is within the galaxy. Here's the galaxy. Just from the fact that things are going around this plate in a circle, there must be mass in there. What is the mass that's inside this thing? Well, we don't know, but now that just means you employ more physicists to come up with wild theories. The theories have to be consistent with everything we know. That's amazing how many things get ruled out. People are always sending me their latest theory, but they haven't checked to see whether that can be ruled out by anything that's known. To be a real astronomer, you have to be able to do that checking, because you find that 99% of the ideas you come up with, you can rule out based on measurements that have been made somewhere sometime. Sometimes people get annoyed that I don't want to be a co-author on their theory and get it published because they can't. But in fact, they haven't done the homework. They haven't done that checking. And that you have to do that because ideas are relatively easy to come up with. Ideas that work are the rare ones. Two of the rare ones that have worked so far, one of them are called massive, compact halo objects, or MACHOs. Massive, M-A, compact halo object. Why is it called a halo? Because the things actually exist spread out over this kind of region. They're not actually within the disk itself. And and what could they be? Well, it turns out planets work fine. Or very dim stars. And it could be bricks. I mean, suppose space is filled with bricks. That would do it. And some of these things now have been observed. They're very small stars. They're observed because as you're looking at a distant star, and one of these things passes in front, you could actually detect the deflection of the light from the distant star. And so there have been observations of some of these things. So there are some MACHOs. Whether they can account for all of this mass, we don't know. But it's a great name. The alternative theory is to assume that they're not macroscopic big things, but are tiny little things, individual particles. Some people once thought they could be neutrinos. But if you work out the neutrino thing, it doesn't seem to be consistent with what we understand about the creation of the universe. Without going into that, let me just say that very few people today think they're neutrinos. But could they be other little particles? Maybe a kind of particle we have never discovered. What are the properties that such a particle would be? Bernard Chatelet in this department is one of the world's experts on these particles. He calls them weakly interacting massive particles. So weakly because they don't feel the strong force. They're like neutrinos, but neutrinos have very little mass, so it's hard to give enough energy to them for them to have gravity. These things would be massive particles, weakly interacting massive particles. WIMPs. It's great that the argument is over what machos or WIMPs. I love this. Weakly interacting. And the nice thing about WIMPs is because they're weakly interacting, they just pass right through the sun and the moon. They pass through us all the time. The main thing they're doing is contributing their mass, like neutrinos, but they're contributing their mass, and by contributing their mass, they provide gravity. So are the WIMP theory right? Well, Bernard is doing this great experiment. It's been going on for a long time. They ruled out all sorts of kind of WIMPs. All you do is build a detector, and you wait for one to hit the detector. Now, it's a lot harder than that because there are cosmic rays and local radioactivity, so you have to get this thing away from everything else that might hit it. You have to get rid of all the radioactivity inside of it. Really difficult experiment. But if you can do that, then you have this box, and eventually one of these WIMPs will hit it, and you'll detect it. And you'll discover the WIMP that is postulated to exist. So those are the two theories, WIMPs and machos. And there are some other theories going around too. I think cold dark matter, hot dark matter. There are several other things that have recently been revived, but the ones I want you to know because of these cute names are machos and WIMPs. Even more so, when we look at the clusters of galaxies, we find that the clusters of galaxies rotating around each other, there's not enough mass in those galaxies to keep these in a cluster. That's a really interesting problem, too. The fact that it's hard enough just to have the galaxy going around, but when a galaxy goes around another, it seems to be even more dark matter. So it works out if you assume that the dark matter is not completely clustered within the galaxy, but that there's a lot of dark matter in between the galaxies. I was asked before class, what is in between the galaxies? And these days we might say, well, WIMPs or machos. And they provide enough within the cluster of the galaxy to keep the cluster of the galaxy together, because otherwise the galaxies are moving so fast they wouldn't be bound to each other. But if you postulate WIMPs and machos, how much mass do you need in these WIMPs or machos? It turns out you need more mass than exists in all the known stars. Well, think of that. Dark matter. Maybe WIMPs, maybe machos, maybe something else. Most of the mass in the universe is made up of material we don't know. Wow. This is why everybody wants to go into astrophysics. I mean, if you want to make a discovery, you want to figure this one out. Boy, but it's a big problem with lots of really good people working on it. And it's very hard to figure out how to even look for this stuff. Mostly it's like careful detective work. You just measure everything. And if you're a good detective, you have a better instinct on what to measure than other people do. It's all out there. You can read the books on machos and WIMPs. You can read all the data. It's all available there. What are needed are not only the right idea, but the willingness to work hard on it to see whether the new ideas are compatible with what we know. As I say, 99% of the new ideas turn out to be no good. That the people who are in this field are just tired of hearing the wild ideas from people that they've already ruled out for other reasons. It takes really hard work in learning the astrophysics. And then making the measurements. These measurements that detected machos were really tricky measurements. They had to look into blank regions of space, look at stars, and look for the star to suddenly be deflected a little bit. as something went by, it would happen very quickly. And they had to keep a record of it, and they had to prove it wasn't instrumental. And they're not going to see that macho again as it goes in front of the star, because it would just went in front of the star once. You happen to be looking at the right star. It deflected because of the gravity of the macho. And you never get to verify that macho is really there, because it'll never pass in front of another star. The odds are very small. You need to have lots of machos and lots of stars to catch a few. So you have to do the experiment so carefully that when the data comes in, you can show it to skeptics and prove to them that this is the only explanation for what's seen. Yes?
Could a big macho ever hit a star?
Well, sure. A big macho could hit a star. I'm not sure we have ever seen two stars colliding. And the reason is it just happens so rarely. Stars are really quite small compared to the space between them. If you look at the size of the sun, it's about 1 million miles across. It takes about 5 seconds for light to get across that. The distance between the stars is like light years. So this thing is 1/110 millionth. If you look at the sun and compare it to the area that you could miss on, this size here is like 1 in 10 million of that, which means the area is 10 to the minus, if it's 10 million, 10 to the 7, 10 to the minus 14. So the odds that something will hit the sun if it's zooming by are 1 part in 10 to the 14th. Really quite rare. The only reason you take the machos is that you don't have to get really, you don't actually have to hit it. You just have to be close enough that your gravity deflects the sunlight.